Hi, my name is Erich Hanke, and I am Principal Engineer of Storage and Memory Products at IntelliProp. Today, we're walking through a demonstration of how to run a Zephyr Fabric Manager and how to do hot add of memory to hosts connected to the Fabric. So the first thing I'm going to do is open a bunch of terminals. Okay, so there's three columns of terminals. On the leftmost column, this is what we call SOC3. We will be running our Zephyr Fabric Manager and a few other tools from this column. The middle column is running on a host, SSH'd into a host that we call SOC4. This is going to be running the Linux Local Management Services, or what we call LLaMS. As well as some other applications. Right-hand side is on a host SSH'd into a host that we call CXL1. So the first thing I'm going to do in the upper left-hand terminal is run our Zephyr Fabric Manager. Okay, so then on SOC4 and CXL1, I'm going to start the Linux Local Management Services. Okay, and also on SOC3. So now that we've run Zephyr, we can see this message from the Zephyr terminal. It says finish exploring Fabric 1. We can take a look at what Zephyr found by running the ls-gen-z tool. Okay, so this spits out a whole bunch of information, text information. Here you can see component information for bridge 0. This is the Fabric adapter bridge that's contained within this CXL3 host. You get a component UUID and a serial number, and then an indication of what state the component is in. So you see two different interfaces. They're both in the up. You can follow the text here to kind of manually see what the topology looks like. Component 2 interface 0 is connected to bridge 0. So if I find component 2, it's this other bridge. Interface 0 is connected to CID 1, which I know is the CID of this bridge here. So that's kind of hard to manually follow through. So we created this utility to draw the topology for us. Okay, so this is a graph that showcases the connectivity of the topology. So this is using a tool called NetworkX that bolts on to the Zephyr Fabric Manager. Zephyr Fabric Manager discovers what the fabric topology is and reports that back to the NetworkX tool. Here you can see three host nodes. One is the PFM, that's SOC3. One is this SOC4, and then one is named CXL1. So the PFM and SOC4 both have two active interfaces that's represented with this green line, and CXL1 has just one active interface. So CXL1 connects all the way down to this switch hemisphere. This switch has 3 active links on it. This switch has 4 active links on it. One of them goes down to this ZMM0 from MB0 1B that connects down to this ZMM1. So we have 2 memory devices, 2 switch devices, and then 3 hosts. So not a particularly large fabric, but it's a representative fabric to showcase some of this capabilities. So I'm going to shrink this down and move it out of the way, but keep it up to the point that we can kind of still see what the topology is, and we can reference back. It's a little squished down, but that's okay. Okay, so the next thing I'm going to do is run ls topo on both SOC4 and CXL1. So ls topo on both of these hosts. So SOC4, you can see, is a quad-core processing system with 3 different NUMA nodes. There's no fabric resources that have been added to this host just yet. CXL1 is an Intel Sapphire Rapids. This is a single socket server configuration right now. You can see that there's no fabric resources that have been added over here either. So close that down. Okay, and then I'm going to run htop to just see we have roughly 4 gigabytes of memory active and available on SOC4 at the moment. So what I'm going to do now is, in this terminal over here running on SOC3, I'm going to run a tool called post Zephyr res, and I'm going to add dynamically a 60 gigabyte DAX resource to SOC4. Okay, so there I've run the script, and I'm going to show you what in that config file. So if you look at the config file, you'll see it's just a single resource, 25 lines to describe that resource. We have a Fabric UUID and then a resource description. Within the resource description, we have producer, consumers, and then more details on the specific resource. So in the producer list, I'm going to run ls-gen-z down here. So in the producer list, you can see the UUID and serial number of a ZMM. So if we look down here, we can see this memory device here with CID7 has a matching serial number and UUID. The consumer here, UUID and serial number, is mapped to this bridge device here, and that's the SOC4. So we're saying present resources from this component to this component with this set of personalities. So this class UUID indicates what driver we're going to bind to it. We can tell that this is the DAX driver. These flags indicate what NUMA node to place that DAX device into. And then we have memory configuration. Here's the starting address, which is represented as offset into that fabric attached memory device, and the length is roughly 60 gigabytes in size. Okay, so now over here, I can run that ls topo command again. And now we can see we have a block DAX 1.1, 59 gigabytes. So right now, this is a DAX device that we can use using mmap or any other DAX specific utilities. And if I do a ls/dev DAX, I can see that device is now present. Okay, so if I run that same command over here, ls/dev/dax, there's no such thing. So then what I'm going to do is run this post res again over in this terminal. But this time I'm going to point it at a different config file called 60 gigabyte DAX CXL1. So what this is going to do is run that same type of configuration, but it's going to push a different region of that same memory device over to CXL1. So if I rerun this command over in this right terminal, you can see now we have a DAX device showing up. And if I run lstopo on the CXL host, you can now see that same 59 gigabyte DAX device. So another thing to take a look at is when I'm running these tests, down here in the bottom, I'm running a debug interface into the two ZMMs, ZMM0 and ZMM1. Since I've allocated resources from the 128 gigabyte ZMM1, you can see that there's a little bit of traffic that's getting sent down to this device. So every second or so, we print out how many packets have been received within that last second. So right now, there is some traffic, but not a whole lot. So we will change that. So now I want you to take a look at this SoC4 that has HTOP running. And again, remember that we have roughly 4 gigabytes of memory. You can see that right in this middle spot. What we're going to do now is take this DAX device and hand it over to the kernel to be used as system RAM. And to do that, I'm going to run this script called DAX to NUMA. So while this is running, you can now see that we're getting millions of packets per second in the lower right-hand terminal down here. And then as that finishes, watch this memory location. It's going to jump up from 4 gigabytes of available local memory, and it's going to go all the way up to about 64 gigabytes. You can see when we're running change mem, we have 62.8 gigabytes of usable memory now. So we basically handed a 60 gigabyte portion of fabric attached memory over the kernel to use as Mallocable memory. Now if I run lstopo again, you can see that that DAX device is gone since we've unbound the DAX driver. And in group 0 of NUMA node 1, we can now see a 59 gigabyte chunk of memory. So this NUMA node, we can target applications to run in this NUMA node. We can make applications run outside of that NUMA node, or we can let the kernel choose where to run the different applications. So I have a set of scripts or program called GUPS. GUPS is a very simple program. It's designed to malloc a whole bunch of memory and interact with that memory. It does memory sets, memory copies, memory comparisons. It runs LFSRs to run pattern randomization, things like that. When memory is malloced, we go through and touch all the memory such that that memory then gets consumed out of the pool of available memory. So I'm going to run this GUPS demo. It runs GUPS in 3 different ways. You can see that here. So the first way is I'm going to run the GUPS demo on NUMA node 0. So I'm going to use the NUMA control utility to bind with a membind flag this GUPS program to run out of the local memory only. When that finishes, I'm going to run the same program, but I'm going to membind it to run out of remote memory only. And the last time that I run the tool or the program, I'm going to use the interleave flag. So this is going to interleave memory across NUMA node 0 and 1. Okay, so here it's running out of local memory. So you can see the memory allocation went from 1 gigabyte up to 3 gigabytes. Now we're running it out of the remote memory. And if you look down here, you can see packet activity in the terminal. We're getting 1.5 million packets per second going on to that remote memory. When this finishes, we're going to run the interleaved version. And when that interleave version, it's going to run out of local and remote memory. So here's the interleaves, and that finished. Okay, so now over on CXL1, I'm going to run a tool, just a bio tool, to do some synthetic read benchmarking. And I'm going to point it at the dev DAX. There we go. So now it's running, and you can see roughly 4 million packets per second. And I'm actually going to start the GUPS program again and see that we're sending traffic from both hosts down to the memory device. And now it's up to 5.5 million packets per second. And while that's running, we can see that we can run transactions from both hosts at the same time. So that was the quick demo. Hopefully that was informative on how to run memory binding, how to take remote memory and hand it over to the kernel to be used as Mallocable memory, and how to run traffic from two separate hosts. Thanks for watching. We'll see you next time.